which is coming under something called as non-parametric approach of machine learning. Okay, so yeah, Shinu, can you please start the recording?
Yes, sir, started.
Okay. So this particular session will be devoted on devoted to these particular Gaussian processes, which is known as a non-parametric approach of modeling for this predictive analytics. Okay, so before going into that directly, so let me just show you something regarding that overfitting and underfitting, whatever I was telling in the last session, and how we can actually pictorially tell. Okay, so let me just describe it here first. Okay, so let me share the slides. Here I'll be writing everything. Okay, so so here I'll be just telling you that what do we actually understand by non-parametric. Okay, or what do we understand by parametric? So uh, in most cases, we are basically interested in so parametric versus non-parametric. Parametric versus non-parametric. How many of you have come across this particular term non-parametric? How many of you have come across this particular parametric and non-parametric? Parametric versus non-parametric. So basically, we are interested in predictive analytics. So main objective is to predict the response. Okay. Now, basically, in case of simple linear regression, okay, simple linear regression means in general case of linear regression. So regression, the model is being assumed as okay that y equals to beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 plus beta p x2 plus xi. This is a model I am assuming. Okay. Now the thing is, what is the basically philosophy behind this kind of model assumption? So has somebody dictated me, or from my own experience, I am basically telling that okay, this will be a linear combination of the unknowns and the knowns, right? And I'll be using this as a base model, or I'll be using this particular model for all of my analysis, and whatever it predicts, I have to take. Statistics, actually, statistical machine learning, or any kind of modeling methodology which are emanating from statistics, okay, they are not, you can say, one must not be satisfied with only one model. Okay, one must not be satisfied with only one model. Okay, and that's why basically Professor George P. Fox quotation is very, very, you can say, useful for this for us. Always we have to remember that all models are wrong, but some are useful. So basically, we have to go for multiple model proposition. Okay, multiple model assumptions we have to go for, and then we have to pick the best one. We have to pick the best performing model. Okay, based on some kind of performance measures, like highest R square, like lowest RMSE, or like lowest MAP. Okay, all these kind of things basically we can do. Now the thing is that we are having three types of or two types of models basically we generally call. Okay, so three types of models. So one is linear regression. So as it is linear, so there will be something called as non-linear regression. Now we can have something called as polynomial regression. I think you might have heard. How are they different? So linearity that can come from, okay, linearity can come from two things. Okay, one is linear in parameters and linear in variables, predictor variables. Okay, so predictor variables, right? Now, when it is linear in parameters, in general, wherever it is linear in parameters, okay, so if it is yes, then we call it as linear regression. Okay, otherwise, if it is no, then we call it as non-linear regression or generalized models, and many kind of names are there. Okay, so I'm not interested in that. We are not generally machine learning. We are not going into this kind of non-linear regression. But the thing is, we are sometimes we are interested in predictor linearity in predictor variables. Okay, so when if it is yes, okay, then we call it as linear regression generally. So we have to check that whether uh, check whether the parameter combinations are also linear. Parameters are also linear. Then we call it as linear regression model. Okay, so then we call it as linear regression model. Okay, but when it is polynomial, so if it is no, okay, then we call it is as polynomial regression. Now let me just give some examples of this particular linear, nonlinear, and polynomial regression. So here, suppose I have a model that I am having y and x1, x2. Okay, this is our data set. Okay, so if I am assuming y equals to beta naught plus beta 1 x1 plus beta 2 x2, okay, then it is a linear in parameter as well as variables. Okay, and when it is linear in parameters, then only generally we call it as linear regression. Okay, now suppose I'm having y equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 1 beta 3 x1 square plus beta 4 x1 x2. Okay, now we will be telling that this is having non-linearity in variables. Okay, but parameters are linear. So whenever it is non-linear in variables, you can assume a new variable. Okay, whenever it is having higher order or interaction between two variables, and we can call it as polynomial regression. Okay, so this is a case of polynomial regression. Okay, Acha. Now if I am having suppose y equals to 1 by 1 plus exponential of minus beta naught minus beta 1 x1 minus beta 2 x2. Okay, this kind of model. Now what is this kind of model? Which regression this is? This is logistic regression. Now in this the logistic regression, what is happening is beta naught, beta 1, beta 2 all are actually non-linear acting on this particular y. So that's why this is a non-linear case. So this is a, I think I have to practice handwriting. My handwriting is getting distorted day by day. So this is non-linear regression. Okay. So where the parameters are affecting, the parameters are acting non-linearly on the y. Is it okay? So is it okay? So this is about linear regression, non-linear regression, and polynomial regression. Now the thing is, all these models, they are actually coming under parametric approach. Okay, they are coming under parametric approach. All these models. Why parametric approach? What do you understand by parametric approach? That I am basically identifying uh, manageable parameters. Okay, manageable parameters for the model, and I am working on that particular data set. So what do you understand by non-parametric? Non-parametric is actually telling you that I cannot assume, or I'm not in a position to go for a parametric approach. That I cannot actually assume the parametric form of that particular model. What is that parametric form? Parametric form is how many betas I can take. I don't have any idea. Okay, or I cannot actually go into that. Okay, so non-parametric, it actually means, okay, so non-parametric, etymologically it means non-parametric. Non-parametric etymologically means there are no parameters. Etymologically means no parameters, but it is infinity parameters scenario. So it is actually infinite parameter scenario. Okay, infinite parameter scenario. Why this is infinite parameters? Where from it is coming from? So where from it is coming? So basically here you are having a limited number as well as a manageable size of parameters. But in non-parametric approach, actually it is free, all free. Okay, so you are doing something in the data set, and it is actually creating a huge set of parameters. It is creating a huge set of parameters, and it is unmanageable kind of. Okay, so as the data, it is dependent upon data. It is not dependent upon that how many dimensions you are having. It is actually dependent upon what is the size of the data. Okay, it is dependent upon what is the size of the data. We will be coming to this aspect, that it is dependent upon size of the data. Achha. What are the different non-parametric approaches in machine learning or deep learning? Take neural network, that is actually non-parametric. Why? Because it is, first of all, it is nested kind of linear models. Okay, so tomorrow we'll be starting this neural networks. Okay, the first session will be Professor Gunjan Soni sir will be taking care of this particular make you understand about the basics of neural networks. Okay, basics of neural networks, and we'll be actually playing with that, right? So in neural networks, actually what happens? So each layer is a linear model, like this linear regression. Now, if you are having multiple layers, that means the layers are actually the linear models are actually nested within each other. Okay, so what is happening, that even if a moderate size of neural networks, okay, neural network, that will also having around 5,000, 6,000 parameters to be tuned. Okay, for that particular model. So what are the parameters there? Parameters are the weights and biases. Okay, weights of the connections and biases. So in you can say in moderate size of networks also 5,000, 6,000 parameters. It's a kind of very natural. Okay, it's a kind of very natural. So that's why I'm telling. So just try to find out that, try to understand that what is the difference between parametric and non-parametric approach. Okay, and here in non-parametric approach, etymologically it means no parameters, but it actually is having infinitely parameters possible. Okay, and that's why basically it is unmanageable. So that's why we are keeping it inside non-parametric approach. Okay, now we'll be looking at something called as Gaussian process-based modeling. Okay, so where we are going for this kind of non-parametric approach. Okay, now what happens in this Gaussian process? So let us just start. So we'll be looking at Gaussian process-based predictive models. Okay, so here what happens that let us start with a data set, simple small data set. Okay, so y, uh, this is x1, this is x2. So this is y1, this is x11, x12, y2, x21, x22, then y3, x31, x32, blah, 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 yn, x n1, x, n2. Okay, so total n observations are there. This n can be 10, n can be 100, it can be 1000. Right. Now what happens that in conventional linear regression, conventional linear regression, we are proposing a model that is y equals to beta x plus epsilon. Okay, and here what is the you can say beta vector and what is the x vector. So y is n cross 1. So beta x or x beta, whatever it is. So let me write x beta, that would be better. So this will be so this will be n cross p, then p cross 1, and then n cross 1. Okay, so what we are doing, we are actually finding out that what is the y hat for each of the case. So this will be y1 hat, this will be y2 hat, this will be y3 hat. This is the predicted values. Okay, so it's yn hat. Okay, so predicted value means y hat means it is beta naught plus beta 1 x1 plus beta 2 x2. This is what. Okay, now we are actually finding that what is the sum square of error, that is SSE. SSE will be I equals to 1 to n summation. Okay, then yi minus yi hat whole square. Okay, this is SSE, and we want to minimize this SSE with respect to beta j equals to 1, 0, 1, 2. Okay, and equating it to 0, then we are finding out this. Now the thing is that here we are assuming that there are actually three parameters of this model. We are actually assuming three parameters of this model. Is it okay? We are assuming three parameters of this model. Now uh, there are two predictor variables. So one parametric form, okay, one parametric form 1, okay, parametric form 1, that is actually y equals to beta naught plus beta 1 x1 plus beta 2 x2. Right. Now parametric form 2 can be y equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x square x1 square. Okay, this one. Parametric form 3 can be y equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 or beta 4 x2 square. This can be another. Now parametric form 5. Okay, so I can have several, this polynomial terms also I can include. Okay, polynomial terms I can include. So then I'll be finding that who is actually having the highest performance indicator or performance measure. Okay, so based on that I'll be selecting that particular model. Now this is basically I'm doing manually. Okay, I'm doing all these things manually. Okay, that I am deciding that okay, here it will be x1 square, x2 square, then x3 square. All these things basically we are having this manually, and based on this manual selection of this particular parametric form, we are uh, running this particular model, and we are checking that how good it is in fitting the data. Is it okay? Now the thing is that this is I want to actually remove this human intervention. Okay, I want to remove this human intervention. What are the ways out? What are the ways out? Suppose this kind of simple linear models you want to create, and Gaussian process will be a very nice way out to don't restricting or not restricting yourselves to a particular set of models. So what is this Gaussian process? So Gaussian process is actually telling you, okay, so Gaussian process is actually telling you, or let me give the formal definition of Gaussian process. So Gaussian process is a random process, first of all. Okay, so Gaussian process is a random process. Okay, so it is a kind of data generating process, DGP. Okay, so random process. Now, whenever it is a random process, then it will be depending upon two things. Okay, that was discussed in Markov chains also. Okay, when Markov chains as well as this thing when it was discussing that sampling method and all these things. Basically, probability measure will be coming into picture first of all. Second is a time effect will be coming. Okay, that at which time what value it is taken. Okay, what value that parameter is taken. Okay, so in this way, basically, random process depends upon two things. One is time, and another is probability measure. So I'm not going into that theory. So basically, a Gaussian process is a collection of yeah. So it is a random process, or formally defined a collection of random variables. Okay, random variables, and they must be possibly they might be possibly infinite in number, possibly infinite in number. Okay, and any finite number of which okay has a consistent a consistent uh, distribution which is joint Gaussian. So it will be a collection of random variables which is possibly infinite in number, and take any set of that. Okay, any set of those random numbers, random variables. If I take a finite number of random variables, um, which will be having a jointly Gaussian, they'll be jointly Gaussian distributed or normally distributed. So that is basically the Gaussian process. Okay, and informally it can be told as, so this is formal definition. Okay, and informally it can be a generalization of multivariate Gaussian distribution, multivariate Gaussian distribution. Okay, uh, um, two of infinite number of random variables. Okay, infinite number of random variables. Or it can be thought of thought of uh, Gaussian distribution over functions. functions. So where these functions are coming. Basically, what is happening? Basically, what is happening that here, if I go back to this simple regression, okay, parametric regression. Basically, what is happening that whenever I am assuming this particular parametric form, okay, then I am creating functions of random variables, functions of variables basically, okay, on the predictor side. So functions of uh, variables means that x1, x2, they are the linear one. X1 square, it is basically the squared one. Okay, x1, x2, that is interaction term. Okay, so in this way, basically, I am creating new features out of the variables. So I think variables and features, you already know that what is the difference. So features are basically modified variables or processed variables. So here what is happening? Now I want to do it blindly. Okay, now I want to do it blindly. So I'll be giving a particular functional form, put your data into that functional form, and then try to create the, the modified data set or the modified, or you can say the feature set. Okay, the feature set. So here what is happening that if you look at this particular parametric form, they are uh, all parametric forms are in original variable space. Variable space. Okay, but basically now what is happening that I want to create an infinite dimensional functional space. Okay, so from the data original predictors, okay, and from that original predictors, I am basically trying to create uh, an infinite dimensional function space. So what is happening here that I am basically taking a mapping. Okay, I am basically taking a mapping that I am taking the original predictors and passing through a particular function, and then I can create infinite dimensional function space. And in most of the case, it will be uh, the 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 feature set. Okay, the feature set will be the feature set will be feature set data will be a symmetric matrix with order n cross n. Okay, order n cross n. So here what is happening that from the original predictors, one side it is the original predictors, and I'll be mapping it or I'll be pushing it through the through one function, and I'll be creating an infinite dimensional function space. Okay, this will be having two advantages. First is that, so advantages of this is that first is that um, the feature space will be infinite or possibly infinite dimension. Okay, second one is that two rows of data, okay, original data can be compared to get distance between them. Okay, so what do this mean? Actually, now I am going to discuss. How many of you have heard of this k nearest neighborhood kind of regression? K nearest neighborhood kind of regression. Okay, so k nearest neighborhood. Okay, what it does, it is basically compares two rows of data at a time. Okay, two rows of data at a time. So two rows of data at a time is compared that whether they are nearer or far. Okay, so compared to find out whether they are similar or not, whether they are similar or not. Okay, so in this way, basically, we are trying to find out. So it is basically, suppose I am telling that birds. Okay, so I want to identify birds. So one side it is swan, another side it is a crow, another side it is a this particular the this what is that called? Those birds who eats actually this fish and all these things. So I'm forgetting the name. So they are also white color. Okay, so swan is also white color. Ducks and ducklings are also white color. Now crow, suppose if it is also entering in this particular group, then you can easily identify that ducks, swans, ducklings, and all these things, they are quite similar, and you can actually group them into a single category. And they are very similar. They are nearer to each other. Whereas they are having huge distance from pro because the features, color, okay, everything is actually different. Okay, so that's why. So this kind of logic is basically behind this particular KNN. Now, KNN is also a non-parametric approach. Here, we are not assuming any kind of parametric form for the model. Okay, if you remember, KNN does not have any kind of parametric form. It is also non-parametric. Okay, but non-parametric, it does not mean that it is having no parameters. It is actually infinite parameters, and infinite parameters, so many, so big parameter space that we are leaving it. Okay, you go. Okay, kind of. Means we are not considering you under this parametric approach. Okay, so same thing actually happens in this Gaussian process also. So now, if you look at this particular data set, okay, so y x1 x2, and here y1 x11 x12 y2 x21 x22, then y3 x31, then x32, then y10 x10 x10. Okay. So suppose 10 data points are there. So I'm taking a small data set so that it will be easier for us to comprehend. Now, what is happening that on the predictor side, okay, on the predictor side, instead of going for y equals to beta naught plus beta 1 x1 plus beta 2 x2, I'm not going into this kind of model. Okay, I'm not going into this kind of model. What I'm actually trying to do, I'm creating a function of these original predictors. So what kind of function? So function is basically, suppose I am telling that I'm I want to create a multivariate distribution. Okay, I want to create a multivariate normal distribution whose mean will be 0 and whose covariance will be the covariance variance. Okay, that will be actually coming from the distance between each two rows of this particular predictor set. So suppose I am trying to do so covariance matrix. So I am telling that f is a function of these particular predictors. Okay, so f xi xj, that will be following normal distribution. Okay, with mean mu and uh, something as the covariance matrix. Okay, covariance matrix. So element is xi comma xj. Okay, and what is this kxi xj? It is basically a distance, square distance, exponentially squared distance between two rows, ith and jth. So if I put it like this, okay, it is coming as sigma square by 2 multiplied by exponential, okay, minus xi minus xj, okay, square by 2. So this is the function. Okay, so this is the function. Okay, that is having two parameters. Okay, two parameters, that is sigma square and another is L. So these are the hyperparameters. So what is hyperparameter? Hyperparameter is parameters of parameters. Okay, so here what is happening, that the parametric model or the model I am choosing, that is non-parametric in nature, and that non-parametric, it is actually infinite dimensional. Now that can be parameterized, that infinite dimensional parametric space can be actually parameterized by two parameters, that is sigma square and L. Now what is the sigma square? Sigma square is called as the diffusion measure, diffusion variance or diffusion measure, diffusion rate. Okay, and L is called as the scale length. Okay, so you can actually explore this. This is also a very interesting kind of thing. So based on this, what will happen, that a covariance matrix K, it will be created, okay, for this particular F, that will be coming as K x1 comma x1, K x1 comma x2 dot dot dot, K x1 comma x10. Similarly, this will be K x2 comma x1, then k x2 comma x2 dot dot dot, k x2 comma x10. Similarly, last one is last row, k x10 comma x1, k x10 comma x2 dot dot dot, k x10 comma x10. So this is the covariance matrix for this particular F that can be calculated. Now, what are these elements are telling? What are these elements telling? So these elements are basically telling you that whether two rows of observation, are they near or far, because here xi xj mod square, okay, so it is actually telling you the distance between distance. So this will be nothing but xi minus xj transpose multiplied by xi minus xj. So this is nothing but the inner product. And on the very first class, I was telling that inner product always tells you the distance between two vectors. Okay, inner product always tells you the distance between two vectors. Okay, now if it is same vector, okay, that is x1 and x1, suppose. So that will be having value as the same vectors, right? So same vectors, this will be xi x1 minus x1 whole square, right? It will be 0, and exponential of 0 is 1, right? And this will be having a quite large value depending upon sigma square. Okay, depending upon sigma square value, it will be a very large value. Whereas if uh, these are the distant one, these are the distant one. So distant one means two vectors are having much more distance between them. So they are not similar. They are actually you can say very different from each other. So what will happen, that it will be creating x. Suppose x1 and x2, they are very different. So this x1 and x2 will be having a very high value. Okay, that will be having a very high value, but this is negative. Okay, but this is negative. So what will happen, that exponential of a negative quantity, that will be having a lower value. Okay, and lower value multiplied by sigma square, that will also be a lower value, will be low. So this covariance will be actually lower than the, suppose one vector distance between the vector with itself, with itself. So that will be having higher value, and if they are not similar, then it will be having lower value. So could you understand the how this particular covariance matrix is being developed? And it is all based on this particular covariance matrix. So now you will be finding that this covariance matrix is not on the dimensionality. It is not on the dimensionality. It is on the number of observations. So I am looking at the rows, not I am looking at the columns, right? And here is the difference between this covariance matrix creation and principal component analysis. In principal component analysis, we are looking at the columns. Okay, we are looking at the columns. Okay, to create the to find out the variance, we are looking at the columns. Okay, but here we are looking at the rows, and the size of this covariance matrix will be same as the size of the number of observations we are having in the data set. Okay, so this will be n cross n. Acha, I was telling about this particular non-parametric thing. Okay, so let me just give you a brief idea of that non-parametric and parametric. Okay, within using that particular code. So this is a polynomial curve fitting code. Let me just show you. So can you see my code file? Can you see my code file? Can anybody please confirm?
Yes, sir, we can see.
Okay. So here what is happening that suppose I am going for simple linear model. Okay, simple linear parametric model. Okay, that is suppose the true function I am using 3x to the power 3, then 2x to the power 2, then uh, x plus noise. Here it is a true function. Okay, by which we are generating the data. By which we are generating the data. Okay, so uh, so here you can actually find out that what is the scatter plot of this data set. Okay, so plt dot scatter y x comma y. Okay, so if I do that, okay, so you can see that it is a kind of means a linear model will not be able to fit this, or you can say linear model will be able to fit, but the thing is that it will be having higher error. Okay, so r square will be very low. Okay, because it is having you can actually assume this as a kind of piecewise linear. Okay, this is called as piecewise linear. So this is called as piecewise linear. Can I draw it here? Draw something here. So, no, I cannot draw anything here. Okay, so this is a kind of piecewise. Okay, so this one, then this one, then this one. Okay, so three pieces of this particular thing, and that can be taken as linear, right? Now the thing is that we are suppose first we are taking a 1-degree polynomial. Okay, we are taking 1-degree polynomial. Okay, so that means beta naught plus beta 1 x. Okay, so then if I fit that, okay, then you can see that the polynomial fit of degree 1, it is coming as this one, right? Now these 3 points and these 2 points, they are not coming into, they are not properly fitted. Second is the curvature, that is also not properly fitted. Okay, next is that if I go for degree 2, okay, so it is taking beta naught plus beta 1 x square, beta naught plus beta 1 x plus beta 2 x square. Okay, then let me see that how it is coming. So you see a little bit curvature has been given. Little bit curvature has been given. So now if we go for 3, okay, third degree polynomial, then it is coming like little more curvature. Getting my point? It is fitting in a much better way. Now degree suppose 4, if I want, then you can see same, almost same as 3. So 5, yeah, again same. 6, okay, same. So you can tell that 3 is the best degree of polynomial, third is the best degree of polynomial, and we can actually verify it from the this thing means from the original equation. So we have taken 3x to the power 3 minus 2x to the power 2 plus x. That is the true function. Okay, along with this, we can actually create some more inside this, but okay, it's okay, no issues. So here, how you are going to decide that Now we know the true form. Okay, we know the true form. So suppose the true form is not known to you. Okay, so you are just looking for a kind of needle in the haystack. Okay, so what will you do? Blind, totally blind. So you have to basically go on increasing the polynomial degree of your model, and you have to check that where it is getting stabilized, where it is getting the best value of the R square or RMSE or MAP. Is it okay? So this is why basically this particular polynomial curve fitting is actually a kind of example. Now this is a parametric model. Okay, this is a parametric model. Here we have to decide the parametricity of the model beforehand, before jumping into the solving the problem. Is it okay? Is it okay? Is it okay? Can anybody please confirm? Are you people there? Okay, so let me go back to this. Yeah, let me go back to this PPT. So what we are doing, so we are interested in going into into non-parametric approach from parametric approach. Okay, and non-parametric means here we are talking about that it is infinite parameters. It is not a single. It is not, and it is actually infinite parameter means it is dependent upon the size of the data rather than the uh, dimensionality of that. Okay, understood? Now, Gaussian process is basically telling you that there are many types of covariance function you can choose. Okay, there are many types of covariance function you can choose, right? So, what are the covariance functions are there? Popular covariance function, this one I told that is actually coming from radial basis function or Gaussian model. Okay, then we can have uh, Laplace covariance. Okay, so covariance functions. And basically, this is the point where kernel functions are actually coming into picture. Kernel functions. I am not going into kernel functions. Kernel functions are a little bit complex to understand. But here, what is happening here, a little bit easier to understand because we are talking about the data and the difference or the distance between the data points. Okay, so lower the distance, higher the covariance, and higher the distance, lower the covariance. So this is just happening. Okay, so first one is the radial basis function. Radial basis function. Second one is Laplace function. And in Laplace function, so from the Laplace distribution, you can actually consider it as that it will be containing modulus. Okay, so Laplace function will be sigma square exponential minus 1 by 2L, and here it will be 1 by 2L square. So here also it will be 2L square and xi minus xj. Okay, so that modulus is inside. Okay, so instead of square, it is modulus. Then here the uncertainty is, so as it is having modulus, okay, as it is having modulus, uh, uh, you can say that it is not that smooth. Okay, the smoothness of this particular covariance function sampling, that's not smooth generation. Okay, so uncertainty here it is piecewise polynomial. Okay, here it is piecewise polynomial, and there is something called as rational quadratic. Okay, so that will be sigma square multiplied by 1 plus 1 by 2 alpha L square mod of x1 minus x2 or xi minus xj, okay, uh, whole to the power alpha. Okay, so here alpha is a free parameter. You need to say, okay. Now it is actually dependent upon. It is actually dependent. As there are some more functions. Matter 3/2, matter 5/2. You can give it a search in Google. Okay, you'll be getting lots of articles are there on this, and you'll be getting lots of information. Right now, the thing is that choice of this covariance is dependent upon data. Okay, so how does your data behave? Okay, how does your data behave? Okay, it is actually dependent upon choice of covariance function is dependent on that. Right now, the thing is, what are the hyperparameters? Okay, so sigma square and L square L. So let me write it here itself. Sigma square and L are the hyperparameters. Means they are the parameters of the parameter. Okay, so sigma square is known as, it is correlation factor, or I told earlier that it is called as diffusion factor also. So correlation or diffusion factor. So what does this mean actually? So how fast the correlation of the data points they are getting vanished. Okay, so how fast, sorry, this is not sigma square, sorry, this is actually L. This is the L parameter, that is the length scale. So this is hyper. So this is L. That is a correlation or diffusion factor. Correlation factor, and it is basically looking at. Sorry, this please correct it. So correlation, it is actually until what distance the correlation, okay, works. Okay, that is basically this L, and sigma square is actually diffusion factor. Okay, so okay, so let us go into that where we are going to, or how you are going to use this particular Gaussian process in our model, in our predictive model. So problem statement is, I am having for the data set D equals to xi yi. Okay, produce a mathematical model to predict y based on new x. That means I want to predict, or I want to produce this particular p of y star given x star, okay, comma data. That is predictive distribution of response for new data point and existing training data. Okay, so this is what we want to find out. Now we can do this particular p of y star given x star comma data can be given as integration of p of y star given x star comma the w, you can say the coefficient, model coefficients. Okay, so we have seen already. So these are W, or you can take it as beta also, no issues. So, and then P of W given the existing data. This is how actually we want to do. So now P of Y star given X star comma W, that will be the likelihood of the new observation. Okay, and P of W given D is the posterior of W. Okay, is the posterior of W. So W you are actually marginalizing out, and you can find out the predictive distribution. Okay, now we'll be looking at, so this will be for D, this produce a mathematical model, and that too using Gaussian process. Okay, and why I am taking as continuous? I can take it for classification also. Okay, you can take it for classification also. Classification is little bit difficult to understand, so I am limiting myself to only regression case. So Gaussian process regression, what it does, that the y, okay, e is actually taken as f of x plus epsilon instead of x beta. Okay, so what is the change here? So conventionally it is y equals to x beta plus epsilon. Now I am replacing this x beta, okay, using f of x, and that f of x is following, okay, that f of x is following something called as the Gaussian process. Okay, and epsilon follows something called as epsilon. Generally, it follows normal distribution, so we are sticking to normal distribution itself. So epsilon is following normal distribution with mean 0 and precision rho. Okay, so precision as rho. So this is the noise, and this is the actual function. Okay, and this is the actual response. Right? Okay, is it okay? So what we are doing here? So first, so if we look at the hierarchy, okay, if we look at the hierarchy, so basically we want to find out what is the uh, what is the probability of W given X, Y, okay, all these things. So we have to find out this posterior, right? So now basically P of Y given F we have to decide first. Okay, P of Y given F. Okay, so this is the actual function. This is the response. What is its distribution? So this is the likelihood. Okay, we have to find out, and we are taking it as following normal distribution. So y, whose mean is f, okay, and it is having variance precision as rho. Okay, so we have already seen this thing earlier. Now we are assigning Gaussian process kernel, okay, Gaussian process on those particular f. So it is Gaussian process with mean 0 and a covariance matrix as x dash. So from practical point of view, so basically uh, y is having t observation, n observations. Suppose. So y is having n number of observations. So n observations. Achha, another thing is also very interesting with this particular non-parametric approach, especially using Gaussian process, that if you are thorough with KNN, if you are thorough with KNN, that K nearest neighbor, so there is one severe problem actually it is being seen. It can be called as a problem, it can be called as an advantage also. So what happens that KNN is called as instance-based regression, okay, or instance-based predictive analytics model. Instance based. What do you mean by this instance based? Instance based means it memorizes all the instances of the data. And whenever you are having this particular, you are trying to see that suppose if you have seagull is a bird which quite similar to the swan, which is quite similar to the swan, but its beak is little bit different from the swan. Okay, it is a kind of flat kind of, whereas swan is having little bit you can say pointed kind of beak. So if you compare this seagull and the swan, then definitely it will tell that seagull is much more nearer than crow. Okay, seagull is much more nearer to swan and ducks, okay, than crow. It will always tell, because crow, if you look at the beak, then it will be you'll be seeing that it is much more pointed. Okay, much more pointed than seagull as well as the swan, right? So here, what is happening in KNN, K nearest neighborhood? The model remembers each and every data point. Now, nearest neighborhood, you have to actually decide that whether you will be going for two neighbors, or four neighbors, or two or three or four or five or six, like this. Basically, you have to go on increasing the number of neighbors. Okay, and you have to find out that by majority voting, that in your neighborhood, okay, what is the majority voting? And if the majority voting as well as the distance calculation between each of the instances with the test data, finding out that who is actually similar, who is it similar with. Okay, so it is actually finding out that the test row, okay, or the test data, who it is similar with. Okay, and some kind of voting is being done. Right. Now the thing is that here what happens in Gaussian process, we'll be seeing it very soon, that the whole data set is actually transformed in terms of covariance matrix. Now, whenever a new data point is coming, suppose y star and x star is a new data point. So x star is the new row. So what will happen that this x star is a new data point, and it will be basically used to calculate what is its you can say distance from all other data points. So this, you are just adding up a new you can say value in the covariance matrix. So here what is happening, that if you look at this particular covariance matrix, so this is 10 by 10, suppose 11th observation has come. So what you'll be doing, that here one row will be introduced, here another column will be introduced, and this will be there will be another element. Okay, so 10 so 11 and 10. Okay, so total 21 elements will be introduced in this particular covariance matrix, which is much smaller than KNN. This is typically no. One thing is that whenever you are going to calculate the this thing kernel matrix, it is costly, but it is not that costly as KNN. Okay, so this is what actually it is happening. And moreover, this is having a proper probabilistic approach to come out. Okay, so that's why this is much more easier, or you can say much more having much more structured approach than KNN. KNN is a truly a non-parametric kind of scenario. Okay, there it is, you are not having any kind of parametricity. So here what is happening, that y is having n observations. So we only consider n unobserved value, for unobserved value of f, unobserved value of f. Okay, that is f is the function that is following gp. Okay, so this is gp, Gaussian process. F as same as x. Okay, so now let us go into the mathematics of this. So p of f is basically here what is happening, as it is following Gaussian process. So p of f, p of f will be following normal distribution with mean 0 and the covariance matrix k. And how this k is calculated we have already seen. So now p of y, okay, that will be p of y given f multiplied by p of f given anything it is dependent upon, that is dependent upon your this thing, that is dependent upon the hyperparameters. So those hyperparameters, if you want to give the priors, okay, then bring it, otherwise you don't bring. Okay, so right now we are not bringing, we are just telling that it is assumed, it is assumed to be known. So here df. Okay, so this is normal distribution, okay, with mean f and rho inverse I n. Okay, and here it is normal distribution 0, mean 0, and k is the covariance matrix, and this is df. Okay, now here comes how to find out this particular integral. Okay, this particular, for finding out this particular integral, long back in the very first day I actually did some kind of I had written one this kind of identity that so let me bring it in. So here, so if this p of y given x, it is given to you, or let us write it from x, okay, step by step. So p of x, okay, it is following normal distribution with x, normal distribution of x with mean mu and variance as gamma inverse, precision as gamma. So variance is gamma inverse. So and I am having something y equals to a plus bx. Okay, so or ax plus b. I am having this thing. I am having a relationship between y and x, that is y equals to ax plus b. So then, what will be the uh, what will be the joint distribution? Sorry, what is the conditional distribution? That will be p of y given x. That will be normal distribution. Okay, with y given ax plus b, comma L inverse. Okay, so if this is the joint conditional distribution, then p of y, that is the marginal distribution, that will be following normal distribution with y, normal distribution of y with a mu plus b, and variance will be, precision will be a gamma inverse a transpose plus L inverse. Okay, so this will be the marginal distribution, and the same thing actually will be being here. So this will be coming as, this will be coming as, this will be coming as normal distribution of y. Okay, so normal distribution of y given mean is 0 and variance as k plus rho inverse I. Okay, and this thing I am assuming as Cn. That is a covariance matrix. Now is uh, Is K known to us? No. No. Uh, as sigma square and the length parameter, okay, L square are to be estimated. Okay, so what happens that how to actually find out all these parameters? So generally in vanilla GP, okay, means without any kind of extra attachment here, in vanilla GP, the hyperparameters are estimated. So parameters are estimated, not predicted, are estimated by maximizing the marginal likelihood. Marginal likelihood. So what is the loss function, by the way? Loss function in GPR, Gaussian process regression. Okay, it will be minus, it will be negative log marginal likelihood. Okay. Now, what is this log likelihood? So this will be minus log loss function. Loss function will be minus log P of y. Okay, so this is minus log normal y given 0 comma cn. Okay, cn. Now this will be nothing but minus n by 2 log of 2 pi. Okay, minus of, okay, so minus of, within bracket I am keeping, minus n by 2 log of 2 pi, my minus half log of determinant of cn minus half y transpose c t cn inverse y. Okay, so this is the uh, log likelihood, marginal likelihood. Okay, so now taking minus on both these things, so n by 2 log 2 pi plus log half log cn minus plus half log, not half log, it is the half of y transpose c inverse y. Okay, now what are the theta here? Theta are basically sigma square, that is the diffusion rate, L square, okay, the length scale, and the other one is the rho. Okay, so these are the parameters, parameters as well as hyperparameters. So now we are actually we are actually uh, we want to we want to estimate the predictive distribution. Okay, so this is nothing but p of y n plus 1th data based on p of y 1 to n. Okay, so that means y1 to yn, based on y1 to yn data, I want to predict n plus 1th data. Okay, so uh, as it is as it is following Gaussian process, so any finite number of variables from y, okay, will follow Gaussian. Will follow Gaussian. Follow Gaussian. Okay. So based on this, now we are going to do this thing. So P of y1, y2, dot, 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 yn as well as yn plus 1, that will also follow normal distributed with mean 0 and variance as C of n plus 1, variance matrix, variance covariance matrix. Okay, now what is the Cn plus 1? How we can write it? So Cn plus 1 will be an augmented form of the Cn. Okay, so Cn, along with Cn, we are just trying to write something that Cn is in the one block. Okay, so along with this, it will be K. This side also it will be K, and this side it will be small c. Okay, this side it will be small c. So just look at this. This is n cross n. This is n cross 1. This is 1 cross n, and this is 1 cross 1. So K is the, what is K here? Covariance between Cn and covariance vector between Cn and the new observation. Okay, whereas small c, what is small c? Small c is basically variance of the new observation. Achha, one thing you should note that Cn plus 1, that is the covariance matrix, it is actually dependent only on x. Here no y will be involved. Okay, so you must remember that. Later we'll be coming to this, and it will be very you can say informative in kind of this. So P of the n plus 1th data point given 1 to n. Okay, that will be, I am assuming that it is following normal distribution mu with mean mu and variance sigma square, sigma, capital sigma. So objective is to compute mu and sigma. Okay, so there are some identities that will be required. I have already written in this thing, but I am not going to write it explicitly here because it will be kind of a very laborious math. Okay, so I am just writing the final. So what are the things that is actually required? That are required is that okay, let me just tell you what are the four. Yeah, screen is still. What happened? Is it moving? Can you please check? No, right now I am not writing anything, but I am changing the slides. Is it changing? Just check whether the slide is getting changed or not. Is it changing? Okay. So let me write down what are the identities that are required. Okay. So identities that will be required are identities will be required are as following. So first is that P of A comma B. Okay, if it is normal distributed with mean 0 and gamma AA, gamma AB, gamma BA, gamma BB. So I think I wrote this in the very first class. Okay, so please look into that. So from that we have to find out from that we have to find out P of B given A. So what is this P of B given A? We have to from the joint distribution we have to find out. So you have to find out this particular conditional distribution. Okay, so this will be I am writing the final result. Okay, so the normal distribution, it will be mean will be gamma BB inverse gamma BA, that will be mean, and this will be gamma BB inverse. Able to see gamma? Not able to see gamma? Acha, okay. So is it because of this color or is it because nothing is getting written? So let me just share the screen once again. Now is it visible, Mr. Amar? Now is it visible?
Only meeting only now it is 1 minute.
Visible?
Yes, it is visible.
It's visible to me.
Acha,
Please
okay.
write something.
Yeah, let me write
Please
it.
write something.
Please, I'm writing in this yellow only. So is it okay? Is it okay?
Not a
Okay.
see. Anyone?
I think then
Let me.
I think then I yeah,
It is
I have
one,
to
I
change
think.
the color. Yeah, I have to change the color. Okay, so let me change the color. Okay, so I am writing it once again. Let me use deep color. Okay, so identities. Is it now visible, Mr. Amar?
No, sir, not see anything.
It's
Anyhow,
visible
I
for
will.
me.
That would be better, I think. Yeah. So identities will be required for computation. Okay, so that will be P of A comma B is given to you, normal 0 with this covariance matrix. So this is actually partition. So from the joint distribution, you have to find out the marginal the conditional distribution. Okay, so this one from this from this we can find P of B given A as equal to normal minus gamma BB gamma BA gamma inverse. Okay, so this is one. Second one is you have to find it out over net. Okay, over Wikipedia, you can give it a search. That is known as Woodbury identity. Woodbury identity. So Woodbury identity tells that if I am having this particular A plus A plus, just 1 minute, let me find it out. It is Woodbury identity. So it is Woodbury identity is actually finding inverse of uh, sum of matrices. Okay, so it is A of A plus UV. I think the inverse of this will be given as A inverse A inverse U Then so A inverse minus, okay, A inverse minus A inverse U. Please verify this thing later. Okay, C plus V A inverse U multiplied by V multiplied by A inverse. Okay, so this is the one. So this Woodbury identity, you please find it out in wiki. You'll be getting it. It's a very well established identity. So we want to find out. So we are interested in finding out what will be the sigma b given A. So that will be coming as C, small c. This will be small c, that is the variance, minus K transpose Cn inverse K. Okay, so that will be the covariance matrix. And mu B given A will be K transpose Cn inverse and then Y star. Okay, so in this way, basically we are happy. So in this way, no, this is not Y star, this is actually, so let me just use this A only. Okay, so using this, we can find out P of Y n plus 1 at data. Okay, predictive distribution I am trying to find out. Based on 1 to n equals to normal distributed with mean K transpose Cn inverse Y1 to capital N. Okay, so check that whether it is coming correctly or not. This will be a 1 cross n. This will be 1 cross n. This will be n cross n. This will be n cross 1. Okay, so this will be 1 cross 1, right? Minus c, that is the small c. Okay, minus K transpose Cn inverse K. So here also this is 1 cross 1. So because this is a variance, okay, it itself means covariance itself, that is giving you variance, and this is coming as 1 cross n. This is n cross n, and this is n cross 1. Okay, so this is also 1. So this is 1 cross 1. So in this way, basically what is happening, the predictive distribution, so the predictive distribution of the n plus 1th observe response observation or response value is following normal distribution with mean K transpose Cn inverse Y and variance small n small c minus K transpose Cn inverse K. Okay, so this is what the result. So this is the Gaussian process regression. Okay, here another thing is to be noted is mean is dependent upon the response. So here mean part depends on Y, but variance part does not depend on. Variance part depends only on X. Okay, so this is what the derivation is. Okay, now just remember this final form or final formula, you can say, and you are enough. You can actually easily you can calculate. So should I give one example for this? I'm having this code implementation for this, but let us just give one example. Okay, so a small, suppose 5 by 5 data points. I have to introduce a new slide. So is my slide visible? Blank slide. So suppose I'm having y and x1 and x2. So this is suppose 1, this is 0, this is 0.5, this is 3.5, and this is suppose 3.2. X1 is suppose 1, 2, then it is suppose 3.3, then 2, then this is suppose 0, and then 1, then this is suppose 2.5 and 3.5. This is suppose 1.5 and 1.5. Okay, so this is the data set. Okay, this is the data set. Hypothetical. Just showing. So suppose the new data, okay, new test data has come as 0.5 and 0.2. Okay, so first what you have to, so what will be the y for this? What will be the y for this? So the covariance matrix, that is Cn. So k, how you will be calculating? Suppose I am using squared exponential kernel matrix, okay, for covariance. So for each of the observation row, okay, so this will be k x1 comma x1. That means variance with covariance with itself. Okay, so that means the variance. Then k x1 comma x2. Then k x1 comma x3. Then k x1 comma x4, and then k x1 comma x5. Okay, then k x2 comma x1, then k x2 comma x2. Like this you are filling it up. Okay, so this will be a 5 by 5 matrix. Now Cn will be k plus row inverse I. Okay, so this row you have to assume to start with. So three things you are going to assume: sigma square, assume, L square you assume, and row also you assume. Okay, and then so sigma square, L square will be required to calculate this kernel values, and Cn will be calculated using this K matrix and this row inverse. Okay, now the thing is, that the x star is 5 comma 2. Okay, so with each of the so this is x star, so k can be calculated as small k. Okay, small k can be calculated as k x1 comma x star, k x2 comma x star, dot dot dot, k x5 comma x star. Got it? So k transpose also you can calculate, and small c will be k x star comma x star. Okay, that is a single layer. Now this will be giving you that so where it will be used? It will be used in this particular the modified Cn. Okay, so here what will happen? The y6 given y1 to y5 will be written as normal distribution with k transpose, small k transpose, from here it is coming, multiplied by Cn, that is the original covariance matrix, multiplied by y1 to 5, comma, small c minus k transpose Cn inverse k. So in this way, basically, you can calculate, and it is little bit laborious to calculate the covariance matrix on all these things, but it's very easy actually to find out. Is it okay? Is it okay? Now we are going to see the implementation, Python implementation of this. Okay. We're going to see the Python implementation of this. So let me just save it first. Otherwise, Shinu, have you started the recording?
Yes, sir.
Okay, okay. Thank you. Okay. So now, polynomial curve fitting I showed you. Now I am going to show a Gaussian process regression. Okay, and a Gaussian process for classification purpose. Okay, so it's just an example. It's not a very big one. Okay, but a small thing. So let us just have a feel that okay, we can do this. So GP vanilla. So what is it doing? So I have written down all the expressions here. Okay, all the expressions I have written down. Please go through. Okay, if you are having any kind of doubt, please come back. So there can be, along with Gaussian process, there can be more other process, Goldstone pullback, then even uh, Brownian motion. Brownian motion is also a kind of Gaussian process, but these are all used in your okay. So GP regression. Right, is a code. I pasted it. Yeah, this one. So here what is happening that some basically I'm creating some here that basis function and kernel functions it is given here. So here suppose this is the data points. Okay, these are the data points. I'm not running this here. So these are the data points, and I want to fit a regression model for this, and then based on that I'll be doing this particular prediction. Okay, so now you can see that I'm using this RBF kernel. Okay, I am using this RBF kernel that is basically kind of Gaussian kind of kernel. It is also called as isotropic kernel regression kernel. So here, depending upon sigma, I can have different types of you can say prediction. So if the sigma I am increasing, then basically vertical on the vertical region, this particular the uncertainty is getting increased. Whereas if I increase the L, then it will be on the horizontal side. On the horizontal side, the uncertainty will be changing. Okay, so sigma square is basically for vertical uncertainty changing, and L is for horizontal uncertainty changing. Okay, so I think I'm not finding the other regression. I did code, but I don't know. It is not showing here. I had GP classification also, classification using GP, but I am forgetting where do they keep. Okay, I'll share the codes with you. Okay, please go through the codes, and if you are finding anything, any problem in understanding, please revert. Okay, so I'm stopping it here. Is it okay? So if you want to leave, you can leave. Otherwise, we can just talk little bit regarding the next two sessions. So in the next two sessions, Shinu, you can stop the recording. You can stop the recording. Yes. Acha. So in the next two sessions, it will not be mathematical. Okay. So you can enjoy that. First of all, second is it will be on a very relevant topic, that will be data visualization. So in data, I think you people all be means whoever is planning to venture into